Kia ora and welcome to the last video in the series Insightful Integration, video 25. Hopefully you found this series really useful, and I hope you enjoy today's problem. This question here I gave to some students a few years ago, and let's just say it's one of my favorites. Not because it's overly difficult, and it is, but the challenge of this problem is the starting. It's a differential equation. We're modeling a context around snow, but the hard part is actually forming the equation to begin with and making some assumptions. If you can make those assumptions and get a differential equation to start it off, it's not too nasty, but it's not your obvious differential equation, which is like NCA problems where a quantity changes at a rate proportional to the amount of the quantity. It's not a typical proportional or inversely proportional question. If you have absolutely no idea how to start the thing off, maybe have a quick sneak peek at the solution before attempting the integration. All the best. Once again, I hope you found this series useful. Maybe drop me a like, subscribe, that sort of good stuff. And we'll see you maybe in the next series, whenever that is. Okay, so the first piece of information here around the snow falling steadily into the afternoon. So I've assumed what that means is that the height that the snow is increasing at is a constant. Height over all of the land, I guess you could think of. So if you've got this, the road, and the snow's coming down, it's going to land on the road somewhere, and then that snow is going to build up kind of like a cuboid. Well, it doesn't really do that, does it? It kind of does more of a mountain kind of shaped thing, but we're assuming that the change in the height of the snow on the road, dH/dt, is a constant, so some constant k. And if that's the case, then the height over time is some linear function, kt plus c. But we're also told that at the time that it started snowing, which is the thing we're trying to find, so let's call that t naught. At t is equal to t naught, the height of the snow would be equal to 0. There's no snow there at that particular point in time. So if we sub that information in to this linear equation, we get that the c value is equal to minus kt naught, or that this height function is equal to k times t minus k times t naught, which is some constant k times t minus t naught. So that's our first equation which we're going to use. That's how the height of the snow depends on time. But of course, the plow is now coming along. The plow is removing the snow, which is also going to affect the height. So we've got the snowplow driving along the road, and we need to model the distance it travels. It says here, the snowplow began removing snow from the road at a constant rate at midday. The snow started falling before midday, and then it got to a point where they realised they needed to get the snowplow out. There's no point the snowplow driving down the road if there's no snow to move it. So at midday, the snowplow began removing snow at a constant rate. But if there's more snow in front of it, it's going to slow it down, because it tells you here that the snowplow travelled 6k from midday to 1, but then only 3k in the next hour. So it's slowed down by the fact that when it's removing it at a constant rate, it can't travel as fast. So what we need to picture here is that if this snowplow, and I really don't want to draw a snowplow, but we'll give it a crack. So we've got and something with a digger in the front, and it's ploughing along, Homer Simpson in the front. The amount of snow in front of it is going to be a factor in how fast it can go. And we've got this width of the road, W, which would be a constant. We're assuming that the snowplow can only plow a certain width of road. It's not like it extends or contracts. And so that's the cross section that we're dealing with here, is like it hits up against a wall here. This is the amount of snow that it can plow at a particular point in time. The speed that it travels at is, or the distance, that it travels at is some function of time as well, and we need to model that. And we're told that it's removing the snow at a constant rate. Now the snow that it's removing, we've got the height of the snow here, h, which is a function of time as well. So our differential equation for this constant rate of removal, which I'm calling alpha equals the constant rate of removal of the snow, is going to be equal to the width of the snowplow, or the width of the road, I guess, if the snowplow goes across the whole road, times the height as a function of time, because that's the cross-sectional area that I've highlighted above in green, multiplied also by the speed of the snowplow. Because of course, if the speed of the snowplow is faster, if it's travelling faster, it's going to be removing more snow, so it's proportional to it. So we've got a differential equation here that we can model the speed of the snowplow at. We rearrange that. We've got dx dt is equal to some constant alpha divided by w times this linear function we found earlier, which depends on time, the height function. Now, we can solve that. It's a differential equation that is separable, or the right-hand side is just a function of time, so we just anti-differentiate both sides, and we get x is equal to alpha over wk, okay, that's just one big constant, times ln of t minus t naught, where t is the time that the snowplow, the time where t is the amount of time that it's been snowing. So that's our x function, and now we can substitute in information to get the constants. So we know that at time is equal to 0, which I'm calling midday, x is equal to 0 because the snowplow hadn't started moving at that point in time. And if we substitute that information in, oopsies, forgot a plus c there, we get c is equal to minus alpha over wk times ln of minus t naught. Now I've dropped the absolute value symbols there because t naught will be a negative. T naught was the time that the snow started falling, and 0 is equal to midday, so it's a negative number. Minus t naught will be a positive number. I don't need absolute value symbols there. The other piece of information we've got is that time is equal to 1, so 1 hour later the snowplow had travelled 6 kilometres. Okay, that was given in the question. 1 hour later it had travelled 6 kilometres, so x would be 6. So if I substitute that information in to the solution, I've got 6 equals alpha over wk times ln 1 minus t naught, and then the c value, which was this dude, now I can use log rules there because I've got 2 logs subtracted, but first up I'll factor out the alpha over wk thing, and then I've got ln of something minus ln of something else, so it's ln of 1 minus t naught over minus t naught. Now the last piece of information is at time equals 2, or 2 hours later, it had travelled another 3 kilometres. so 9 kilometers in total. So I can sub that information in to my equation. 9 equals alpha over WK. Now, alpha over WK, I've just actually worked out what that is because I can see it's there and just rearrange that equation so I can eliminate some stuff. So alpha over WK is 6 over log of 1 minus T naught over negative T naught. Then I've got ln of T minus T naught, and in this case T is 2, plus the C value, and the C value was minus alpha over WK again. So 6 over ln, this is getting messy, times ln of minus T naught. Okay, now I need to solve that equation for T naught. So I'm going to times everything through by the denominator stuff, the ln 1 minus T naught over minus T naught thingy. So I've got 9 ln 1 minus T naught minus T naught equals 6 ln 2 minus T naught. 6 is also a common factor, so I could divide both sides by 6. It's probably a good thing to do. Minus ln of negative T naught. And now there are logs on both on all of the terms. So if I take the 9/6 up the top, up to there, and then use log rules on the right hand side, two logs divided because there's a subtraction there. Now I can cancel off the logs on both sides by taking e to the power on both sides. And now I've just got to decide how I solve this problem. So 9 over 6 is 3 over 2. So if I square both sides, I'm going to end up with 1 minus T naught over negative T naught all cubed equals 2 minus T naught over minus T naught all squared. And this looks like it's nasty, but I can do some simplification here. So the minus T naught cubed on the bottom of the left, and there's a minus T naught squared on the bottom of the right. So if I cross multiply this thing, T naught squared 1 minus T naught cubed is equal to minus T naught cubed 2 minus T naught all squared. Can divide both sides by T naught squared because T naught doesn't equal 0. That's the initial time that the snow began to fall. It's a negative number. So if I cancel both sides of that and just be left with 1. Actually, that's really dodgy setting out. I won't do that. I'll just rewrite it. Now it is a cubic equation here that I need to solve, so I expand out the cubic. 1 minus T naught cubed is 1 minus T naught, 1 minus T naught, 1 minus T naught, or I could use binomial theorem. And then this one is 4 minus 4 T naught plus T naught squared. At this stage I probably have dropped the T naught and just carried on writing time. Okay, so 1 minus T naught cubed is 1, because 1 cubed is 1. We've got minus T naught times 1, 3 of them. We've got minus T naught times 1, 3 of them. And we've got minus T naught, just 1 of them. On the left-hand side. You can see that the T naught cubeds cancel. And then if we rearrange this, we've got a quadratic equation. T naught squared minus T naught. I'm moving everything to the right-hand side. minus 1 equals 0. And then solving that either using the quadratic formula or a graphics calculator or something, we get T0 can either equal minus 0.61803 or 1.618. So now it's got to be a negative number, so we're looking at the first one being the answer and the second one not being the answer. And it's in hours, so minus 0.61803 times 60 is the number of minutes before midday, before the snowplow set off on its journey. It comes out to be around 37.1 minutes before midday. Okay, so in terms of the time it started to fall, the snow started to fall at 11:23 a.m. Of course, there's some assumptions in modelling the situation. There always is when we set up a differential equation to make some assumptions around what the variables, how the variables are related. Like in this particular question, I'm saying the speed of the snowplow is proportional to the amount of area of snow that's in front of it, and the area of the snow in front of it is proportional to time, because the snow is falling at a constant rate and it's building up, although the width of the snowplow is constant. So all of those assumptions there were pulled out of the word problem. Usually in an NCA question, the differential equation you're using is given to you, or it says you can assume something like proportionality. In this question, it was a very open-ended problem, and I'm sure there's other ways of looking at it, but this is just one of those ways. Is 11:23 a.m. the correct answer? Probably not. Is it a good answer? It seems reasonable given the limited information we had, but then again, snow falls in complex ways. Like all word problems, they're a little bit more complicated than the simple models we use to solve them.